All right, we're good to go? All right. So I'm going to continue on from the last part of the 2 talks ago and a good part of the last talk, talking about and specifically focusing on polaritons in these 2D materials. Because these types of materials provide some really unique opportunities, from their high anisotropy to their tunable gate tunable electron densities. So it can provide a lot of unique opportunities that can be observed in bulk materials to many cases, but in much more difficult situations. So originally it was listed that I'm at the U.S. Naval Research Lab. That was true until two Fridays ago. I'm now a faculty member as of last Monday at Vanderbilt University. So I don't have a group. So if you want my picture, this is it. We're starting to grow that group. So hopefully next year I'll at least have one more person standing beside me. I know at least I'll have a postdoc who's starting in a couple weeks. So yeah, so when we think of 2D materials, and we think of, this can also be generalized to more bulk materials, there's a broad range of these different types of polaritons. So this begs the question, what in the world is a polariton, right? So you saw this in the last couple talks to some degree, in particular focusing on plasmon polaritons. It's more generally, a polariton is just a quasi-particle that is a coupling between a photon of light and a charged particle. So when most of us think of charges, we of course think of electrons, right? So this is why plasmon polaritons have been studied for a couple decades now, or multiple decades if you go back to metals in the 50s and 60s, right? So if I do this, right, I can have light, long wavelengths of light coupling to these charged particles, and I can create a plasmon polariton. So why would I want to do that? Well, I can take this very long wavelength of light, and I can compress it down to wavelengths that are on the size scale approaching that of my charged particle, right? So now I can take this free space wavelength of light, which would have had a diffraction limit. Let's say we're working in the infrared, which is going to be most of what we're talking about today. Microns, tens of microns. And now I can focus this down to size scales that are on the order of nanometers, tens, hundreds of nanometers, right? So now I can get around the diffraction limit, and I can start to manipulate light approaching that nanoscale, right? You can also change this type of charge, right? So of course, an alternative type of charge is ionic charges on a lattice, for instance, right? And this is something I've spent a great deal of time studying. If I couple to a polar lattice, I can create a phonon polariton, right? You can also look at electron-hole pairs and look at exciton polaritons, which I just learned is a really nice paper just came out for the first observation of this, I believe in moly disulfide. You can also look at the potential for Cooper pairs, for superconductors, looking at a Cooper pair polariton. You can go to spin and looking at magnon polaritons. There's a whole suite of these types of different modes, right? But for the context of today, I'm going to focus on these 2 predominant types where we actually have a good deal of discussion. And since this is a summer school and not just a highlight of my work, I'm going to focus purely on some work that's been done in graphene, which almost is exclusively not mine, and some work in Borne nitride for phonon polaritons as exemplary materials, and then kind of show you how it can branch into some of these other material systems. All right, so how does a surface plasmon polariton work? All right, well, let's take the simplest case. We need free charges, right? Conduction electrons. So let's just look at a metal, and perhaps the most widely used, or the best plasmonic metal is silver. The most widely used is probably actually gold. But let's think of silver. We have a large number of free carriers. If I take an incident electromagnetic field in the form of light, I can induce these electrons to oscillate, right? Create a coherent electron oscillation. And by doing so, I've set up a surface screening field, right? And this is why this repels that incident light, leading to a high reflectivity. This is why metals are so reflective. This corresponds to a negative real part of the dielectric function. So if we're thinking of finding materials where I can support a polariton, it's this negative real part of the dielectric function that's the mathematical requirement to create a polariton, or to be able to support a polariton, right? So as soon as you have this, you can then say, all right, I can confine light to subdiffractional dimensions. I can create these polaritons. And if I'm thinking of the infrared to terahertz, most of the time we're talking about looking at highly doped semiconductors, or in the case of graphene, of course, a zero bandgap semiconductor, right? Or a metal. So these can take a couple different forms. You saw before, this can take localized form of resonator. I'll show you a little bit of that in a couple slides, or a little bit. There's also the idea of creating propagating modes, waveguide-like modes. Except now, instead of having this mode propagate through the material, it's propagating on the surface, right? So you have this electromagnetic field, this polariton, that's stimulated. It's basically a surface charge current. So you have this field that's bound to the surface, right? But you have this evanescent extent, as we saw a couple talks ago, of the field, where it's actually exposed to its environment. All right? This is where you have the plasmon actually do work. You can do things like surface enhanced Raman scattering. You can have it interact with its environment to modify emission. Or you can scatter this back out in the form of a waveguide to then read back out that information, right? So the idea is you can get this to propagate extended distances. Not just distances, but extended distances. One of the main drawbacks that we found is that there's a lot of issues with loss and how far this can propagate. But certainly waveguides have been demonstrated with propagation lengths that are reasonable for many potential applications. And also you can look, of course, this plasmon carries the information of the photon. So if you read it back out, you basically get the energy of that photon, the polarization, these things, right? So I just noticed as I was going through this, there's actually a mistake here. I'm showing you the dispersion relationship for a phonon polariton. I just think this would go from DC up. This is a plasmon polariton, but the concept remains the same. The first thing you should note, and I'm bringing up these dispersion relationships because we've seen this a couple times, and pretty much if you go through the literature in trying to understand polaritons, this is going to come up over and over again, right? So what does this actually mean, right? Well, it means my momentum here is basically the inverse of my plasmon wavelength, right? So if I'm deep out here, I have a really small plasmon wavelength, and therefore I have a very high confinement. So why don't I always just work here? Well, there's a problem. My light line goes right here, right? So basically, here, sorry. I don't know why it's not showing up here. The light line is linear, right? So there's going to be this momentum mismatch. But if we ignore that for a minute, I basically can go from, if I launch a polariton at this frequency, right, I'm going to have this wavelength, right? And an evanescent field that's going to extend a good distance above. As I push down deeper along this evanescent extent shrinks, and so does my polariton wavelength, right? But this also means, like I said, a bigger mismatch, momentum mismatch that I need to overcome, right? So to be able to achieve this high confinement, we need to have these high K modes. So how do we actually get there? Well, like I said, you have this momentum mismatch. So if I conceptually visualize this, I'm going to let the photon be played by a Ferrari. I'm going to let my charge be played by a Model T. You already know what's going to happen. I get them off at the starting line, and they're never going to meet, right? The Ferrari's gone. So to be able to get this to occur, I need to slow the photon down. I need to get this such that I can put a speed bump here and slow it down so they can match up, come together at the same point at the same time, right? So where can this speed bump come from, right? Well, I can induce a higher index prism, right? Or induce a grating whereby I can take this light line and tilt it, right? And in so doing, I'm basically hitting different areas along this curve. This is how, like, Kretschmann geometries, where you're coupling through various angles through a prism, can allow you to map out this dispersion. Or you can look at things such as nanostructures. And this is probably one of the most used methods when you're talking about these 2D materials, because this is the basis for how you can use scanning near-field optical microscopy as well as making nanostructures to actually add a single K per structure. So yeah, we have this whole suite of materials. Let's talk about scanning near-field optical microscopy as a means for actually exploring these guys in these two contexts, right? So here, I have my plasmon polariton dispersion. How does this work? Well, I'm going to shine light at a given frequency. This is going to be a monochromatic laser, usually a quantum cascade laser, sometimes a CO2 laser. And then I'm going to tune this frequency and make a measurement at each one of these positions, right? So if I stop here and I'm measuring here, I can look at an interference fringe. And by doing so, I can then measure my plasmon wavelength directly. And by doing so, determine what my momentum is, right? If I do this at a bunch of different frequencies, you can potentially map out this dispersion. All right? So this is basically like taking a rock and throwing it in the, in a pond, and you see these ripples coming out. So ideally, you could have a metallized AFM tip. This is the basis for SNOM, or scanning near-field optical microscopy. Or I can have my light come in, scatter off this nanostructure, right, and stimulate these polaritons on the surface. Problem is, I need something that can measure out that, right? So I have to have this guy sitting in one place. I would need a second tip that sends scanning. This isn't really realistic. It'd be very complex to have these two very close proximities, considering you're talking about micron separations. So another way to get around this is just use something else. Use the edge of one of these 2D materials, or a nanostructure, right? Whereby you can launch from your tip. It can basically propagate out, reflect back, and now by looking at that interference pattern that's created from the launched back reflected light, you can measure out that polariton wavelength. Basically, the distance between these two interference fringes is half the wavelength. And by doing so, you can make, say, graphene ribbons. These are triangular-shaped ribbons that were used by these two groups almost simultaneously back in 2012 to do the first mapping of graphene plasmons using this technique. And basically, what they did, you then scan this AFM tip over the surface with a constant infrared light source, scattering these light guys off, and you can get an interference pattern. And you can find you get polariton wavelengths that can be 80 to 200 times smaller than the free space wavelength, right? Now, this is really interesting and exciting because of the fact, if you really think this through, I have a 1 atom thick layer that's strongly interacting with a 6 to 10 micron wavelengths of light, right? So not only are you confined to these small dimensions, you can have strong light matter interactions with a 1 atom thick layer, right? And I guess more importantly, you can kind of look at these images as a way to actually explore some of the physics of these systems, right? So let's look again in a little bit more detail at this, right? So here's my dispersion relationship again. The other thing to point out, of course, is by changing the carrier density, or the Fermi energy, I'm tuning this dispersion relationship. So one of the other really fantastic things that these two groups did, this is Dmitry Basov's group, as well as Frank Koppen's group with Rainer Hillenbrand, they not only measured out these interference fringes, they did this as a function of gate bias at the same frequency. So by sitting at a constant frequency and then changing the gate bias, they're effectively changing that Fermi energy, and then you're mapping out the change in the dispersion relationship as a function of that Fermi energy, right? So now you can see you can get tunable plasmon wavelengths, and therefore evanescent extent and propagation lengths strictly by changing the carrier density at the same frequency. And now this has been more generalized to looking at highly doped semiconductors and things like that, where you've been able to do this to some degree, but typically at much longer wavelengths. So what's the state of the art? Well, there's been, Frank Koppen's group had a really nice paper, going almost 2 years ago, where they, like most of the work in electronics, had demonstrated that by encapsulating this graphene layer within Borne nitride, you could get dramatically reduced scattering effects for the graphene plasmons. And by doing so, you could actually amplify the lifetimes from tens of femtoseconds, which is typical for plasmons, upwards to 500 femtoseconds, right? This is approaching lifetimes that you typically see for optic phonons. So this is pretty much a really extended lifetime, right? So to put that in context, instead of having a few cycles before of polariton wavelengths before this would decay, they're effectively observing this oscillating for 25 cycles. All right? So this means a good deal extension in the propagation length before it decays, while also maintaining this high confinement. Whereas usually when you're looking at, I want to get a longer propagation length, I'm going to go to lower K, so I have a higher evanescent extent at the same time. So I'm losing confinement to get that longer propagation length, right? And you'll use things like metal insulator, metal designs such you can compress that and kind of force the confinement of that light. Here you're doing it naturally just because of the fact that you've reduced the scattering processes. And I don't have a slide for this because it's not, I guess, hasn't been published out, but Dmitry Basov actually just showed from his group low temperature measurements where they actually measured graphene plasmon propagation that was actually ballistic. Basically, it was propagating larger distances than the flake itself. Which is pretty impressive to actually see this in a plasmonic system at this point, because we've talked over and over and banged plasmonic loss to death. And now you can see that there are potentially, you may not want to operate a device at 4 Kelvin, but certainly shows that there's some really impressive physics that can be explored. So I've kind of used graphene to this point to explore and explain plasmonics in the propagating plasmon sense. You can, of course, look at a broad range of materials. This is from a review article I have with Tony, as well as several others, including Tony Hines. You can see this is your confinement, this is your loss, or your damping, basically. You can see a broad range of various tuning capabilities. For instance, molybdenum can give you plasmon operation of a very broad spectral range. Black phosphorus gives you this anisotropy. If this could be demonstrated for a plasmonic system, this would be really cool. This could give you something like a natural in-plane wave plate within atomically thin layers. So there's a broad range of things that are ready to be explored strictly by going through this 1,173 different configurations of these 2D materials, right? So I'm going to kind of breeze through this part on the graphene side of things a little bit faster. This is, you can also look at a localized plasmon, right? The one thing I like to look at, of course, you can take this surface, turn it into, say, a spherical particle. You get this resonant condition. The one thing I always like to look at is, if you think of the absorption cross-section of this, it basically breaks down to these terms here. And the key points I want to make is this: if this is a sphere, then you're going to have this geometric factor of 2. Change the structure, it's going to be a different number. But it's defined by the structure you have and its size. You then have the ambient environment, right? So if the permittivity of that, so let's say we're in air, this is going to be 1, right? Everybody should immediately know that because I have a metallic system with a negative real part of the dielectric function, there's a possibility and a given point in frequency domain where this is going to counterbalance that. For a spherical particle in air, -2, right? So now you have a 0 in your denominator. This blows up. It's a singularity, right? This is the very definition for a resonance and can give you the ability to get these really large electromagnetic fields confined to small volumes. But here's where I go back again and say, all loss isn't bad. If you didn't have any loss, which is this imaginary part of the contribution, this would truly be a singularity. It wouldn't be observable. You basically need loss to give it a line width, right? Some absorption that allows you to actually observe this effect. So too much loss? Well, it all depends on your application. If you want something to be highly absorptive, you want a high loss. If you want something with a broader bandwidth, you might want high loss. It all depends on what you want to do, right? All right, so you just basically need to take what nature gives us, engineer it to make it work for the applications we want. And of course, now you can design these guys to meet whatever you want. You saw this already, so I'm not going to belabor this too much, but one of the very interesting things is, of course, you can take this dispersion relationship and now cause these splittings because of the strong coupling with these interference effects between optic phonons and the plasmons within these materials, right? So, all right, let's take another step. This one at least has not been talked about today, so I'll focus on this a little bit more. These are the phonon Polaritons, right? So how does this work? Well, I'm going to use silicon carbide as an example because this is probably the most exemplary material that's been used for these types of systems. If we look at, this is not an actual rigid thing of the lattice, but let's just say it is. You have because there's 210 different polytypes to consider. But if I just take a generic lattice and say, all right, there's a charge imbalance because it's polar, right? There's differences in electronegativity. So there's going to be a partial positive charge here, partial negative charge here. So if I can induce a coherent oscillation, in this case a coherent lattice oscillation, which can be done in the form of an optic phonon, I now have moving charges in response to light. This can set up the exact same thing as a screening field in a metal, right? Except now it's being done by optic phonons. So instead of working at any frequency less than the plasma frequency, now it operates only in this bandwidth between the LO and TO phonons, the longitudinal and transverse optic phonons of the material. So you can see those for the Raman spectra here in black. And again, just like in metals, you get this real high reflectivity. This is what's referred to as Rastron band. This is actually in many materials more reflective than a metal at the same spectral range. So these can be extremely reflective and have also this negative real part of the dielectric function. So again, you can confine light to subdiffractional dimensions and do so by creating these polaritons. But you'll note the permittivity equation is now quite different. Instead of being driven by carriers, this is driven by phonons. So that has a couple real implications. I've already told you one. You have a reduced bandwidth that only works between these two phonon frequencies. that naturally implies that you have a fast dispersion. So what does that mean? Well, it means your permittivity is changing faster than it would be for a plasmonic system. And since the group velocity, or the speed at which this polariton is going to propagate, is dictated by the group velocity, which is the derivative of this, it's going to be very slow. So in comparison to plasmons, these will not go very fast. They're going to have a very long residence time wherever they are. That can be good or bad depending on what your application is. For a waveguide, that's not necessarily so good. The positive part of this is these are still optic phonons, so your damping is dictated by optic phonon scattering, which is usually on the order of picoseconds to tens of picoseconds. So your lifetimes are drastically improved. About an order of magnitude over graphene, orders of magnitude over plasmonic systems, right? Most plasmonic systems. And this bandwidth can be partially overcome by just changing materials. Now, these are all not 2D materials, but you'll certainly see some, gallium selenide, boron nitride, which I'll talk about a great deal, tungsten sulfide, and all these, right? Basically, if it's polar, it's potentially possible to support one of these modes. So we're talking about 2D materials and phonon polaritons. I haven't shown you a single 2D material yet for these. I will in just a second. The key thing to think about, though, is that these are all layered materials. So they're going to be very, very high anisotropy, or very highly birefringent, right? The permittivities along orthogonal axes are going to be different, right? So basically, if I take silicon carbide as an example, right? Here's this crystal structure for 4H silicon carbide. If I take light from this direction versus this direction, it's going to have a different permittivity. It's going to slow the light down at different rates, right? This is birefringence. If I look at diamond, for instance, it's isotropic, it doesn't matter, right? So you can see that clearly in the visible. Shine white light on a gemstone of silicon carbide, which is moissanite, versus diamond. They both refract the light, but because of the birefringence of silicon carbide, you actually get this prismatic effect, right? So forget everything else I'm telling you today. If you're buying a gemstone or a ring, get silicon carbide. It's a lot prettier. It's a lot cheaper. No politics. So at least I've taught you something today. So if you take this a little bit further, you can say all these materials are going to be birefringent, for sure. Between the z-axis and the xy plane, it's definitely going to be birefringent. There's also this interesting type of birefringence, or more interesting, there's an extreme type called hyperbolicity. And it turns out our exemplary material for phonon polaritons, boron nitride, is such a material, right? People have spent a great deal of time in metamaterials doing these layered stacks, metal dielectric, or embedding metal nanowires in dielectrics to create these systems where you can get this strong anisotropy where the in-plane permittivity is negative, say, and the out-of-plane permittivity is positive, right? Or vice versa, right? And by doing so, you can get these really interesting modes that I'll show you in a couple of slides. All the while, though, we had natural materials such as boron nitride staring us in the face. So because of this covalent in-plane bonding between the boron nitrogen atoms, this van der Waals bonding out of plane, you get this high anisotropy that gives you two Ristron bands, right? Because of the differences between the in and out of plane optic phonons. And in this upper band, the real part of the dielectric function is negative. The out of plane is positive. Well, the lower Ristron band is different. So not only do you see hyperbolicity in a natural material, you see both types of hyperbolicity in a natural material, which is really pretty interesting. So if you think of that conceptually, it means it's acting as a metal and dielectric at the same time, at least as it pertains to optics, right? So what does that actually mean? Well, if I look at what's called an isofrequency surface, this is basically saying I'm fixing the frequency, right? What is my polariton wavelength going to look like? Well, if I have an isotropic material at a given frequency, I can have the mode propagate in any direction. The pointing vector, the wave vector can go in any direction, but it has this limit, right? You saw in the dispersion of graphene, I'm at a single frequency, I get a single K, right? Single confinement. If I look at these hyperbolic systems, that's no longer the case. Here's the lower band, here's the upper band of boron nitride. You have this hyperboloid shape, right? Which is where they get their name. And at a single frequency, you could support pretty much any K, right? Which means now you can confine light to infinitely or arbitrarily small dimensions with only loss as your limitation, right? But there's another interesting jump here, and that is the group velocity and the pointing vector are always going to be tangential to the surface. So at a given frequency, that's going to be fixed. That means the light can only propagate at one direction, which is one of the really interesting things about these systems. So the first studies, again, we're going to go back to SNOM. This is from Dmitry Basov's group again. You can see these beautiful interference fringes that were created. These are the experiments. This is some simulations at different frequencies. And again, by looking at this periodicity as a function of frequency, you can map out that dispersion, right? So here, this is all these different frequencies they measured. Here's a function of distance, so basically from the edge in, what does this interference fringe look like? And you see something really interesting. Of course, I draw a line through it at a given frequency. As I look at different thickness flakes, I get these different wavelengths. And again, if I measure from here to here, that's my Polariton wavelength, right? So then I could take that, take the inverse, and compare that to the incident frequency, and I get my dispersion curve just like I had in graphene. But there's something else here, right? You do the calculation for this, and I have all these additional branches. I no longer just have a single dispersion curve, right? And these are something I'm going to get into in the next slide, because I also want to point out that just like Borne nitride, just like graphene, you can also support this in really thin materials as well. So most of what I'm going to show you is what we'll call nanometric, tens to 100 nanometers or so flakes. But they were able to observe this in 3 monolayer thick Borne nitride as well. In that case, this can go down to the monoscale limit as well. So one of the things I pointed out to you is that you could support arbitrarily high K, so arbitrarily high confinement, but it comes at the, I won't say cost, but at the function that the angle of propagation, the pointing vector, it's only going to propagate at a given direction, right? And it turns out that the angle with respect to the z-axis is this theta, so the tangent of that angle is directly proportional to the ratios of the two permittivities, the in-plane and out-of-plane permittivities. So note back, these are dispersive materials. So one of these, depending on which band we're in, is going to be negative and highly dispersive, changing with frequency. The other is going to be positive and constant, right? So that means this angle becomes a function of frequency. And if I look at this, I can calculate out, based off of the extracted dielectric functions that we have. This is some work I did with Thomas Taubner's group. You can see how this angle of propagation is going to change as a function of frequency in the lower and upper bands. You notice they're opposite, and this is something that comes from this type 1 versus type 2 behavior. All right? And so what does that actually mean? Well, if I have a scattering center here, let's say a gold disk, near the TO phonon in the lower band and the LO phonon in the upper band, the light's going to be scattered off of here. It's going to launch a polariton, and it's going to propagate basically pretty close to directly normal to the surface, straight up, right? Close to 0 degrees. If I change that frequency without doing anything else, this is now going to propagate at these other distinct angles. So basically, as I change the frequency, I'm tuning how this is propagating out, and therefore modifying what my image would look like. So I promised you a couple slides ago that I would explain all this stuff. Well, here's my slab of Borne nitride. Here's the dispersion relationship. This is for a 300 nanometer thick flake. You can describe these modes as transverse magnetic. They're deeply subdiffractional, so they're going to be transverse magnetic in nature. And they're going to have 3 quantum numbers, right? Now, you can only optically couple to m equal 1, and you're only going to be able to optically couple to r equal 1, right? So unless you're looking at dark states and things like that, we're just going to ignore them and call this TM1. And then you have this modal index, right? So here's my first order mode, here's my second order mode, here's my third, fourth, so on and so forth, right? So what does that actually mean? Well, if I look at a single frequency and I looked at each one of these modes, I launched my polariton. They're all propagating at this distinct angle. That's dictated by the frequency or the ratios of these permittivities. However, these modes are going to be replicas of each other, higher order replicas of each other. So you have a single, 1 wavelength, 2 wavelengths, 3. So you're basically compressing along that same angle these modes in that same thickness, right? So now my wavelength is much, much smaller as I go to each one of these high order modes. Bless you, right? So in essence, if I think about that, it just means my polariton wavelength divided by L reaches some fixed value. And I'll also point out that this is going to be thickness dependent, and you'll see that on the next slide. Now, if I take this the other way and I do a cross section this way, I'm looking at constant wave vector, so constant confinement. So my polariton wavelength has to stay the same. So what does that mean? Well, it means they're now going to occur at different frequencies. So to meet that requirement, this is going to tilt the angle at which it's propagating. So now, to get these multiple wavelengths fit in, it's going to tilt to do the same thing. So it's basically like having a Fabry-Perot cavity, except now the polariton of interest isn't the free space wavelength, it's now this polariton wavelength, right? And this is all because in these hyperbolic systems, these modes are confined in the volume of the system rather than to the surface, right? Like you'd see in a plasmonic system, for instance. So what happens when the thickness changes? This is the dispersion relationship I showed you on the previous slide. If I now cut that in half, I now have a 150 nanometer thick flake, right? You can see how the dispersion relationship changes. It kind of spreads out. I now can look at this. Everything else is nominally the same. I take a constant, measure this at a constant frequency. I'm still fitting this in, except now my thickness is halved. Therefore, at the same frequency, my polariton wavelength has to be smaller. And therefore, I've arbitrarily forced higher confinement just by making this smaller. So you can arbitrarily continue this process, right? Go to 100 nanometers or take this down to the 1 atom limit. Of course, as you get to a single monolayer, you're only going to have a single branch. There is no volume modes anymore. This is all surface. However, this is just going to keep tracking down and approaching that of the TO phonon, right? And giving you higher and higher confinement all the way. But what happens when I go towards bulk, right? Well, now, if I have thickness approach infinity, I can now get basically a continuum. This is like going from 2 atoms up to a crystalline species, right? You're getting all these modes coupled together, hybridizing, and then you end up with this continuum of modes where you really can't even differentiate between any of these once you get to this. And this, of course, makes sense if you really think about it, because now as I go to the highest thickness, I can support any wavelength I want because my polariton wavelength is so much smaller than this thickness. So I told you there's this one problem. I have my plasma on here, which moves really, really fast, but dies out pretty quick. I have this phonon polariton, which lives a long time, but moves really slow, right? So how can we overcome this? Well, just to prove how slow this really is, there's this really nice work from in Borne Nitride from Rainer Hillenbrand's group, where instead of, if you remember back with the SNOM, to be able to do this, you had the 2 tips you could potentially do, which is conceptually makes sense. You have one that's scattering and the other that's measuring. It's not really realistic. But if I take my static tip and I replace that with an edge, a gold edge, I can now launch the polariton off of this, and then I can measure this propagation as a function of time by moving my tip in relation to that. So instead of setting up an interference pattern, I'm looking at this polariton launch off the edge. So now the peak to peak is actually a wavelength instead of a half wavelength. So if you look at this as a function of time, right, and this is the distance from this gold edge, you can see these modes propagate away from the surface, away from that edge, and by tracking the rate at which that happens, this envelope velocity, you can measure the group velocity, or the rate at which it's moving. And in the upper band, this is about 27/1000ths the speed of light. In the lower band, it's actually 2/1000ths the speed of light. So extremely slow. So if you're trying to do something like create a waveguide and get really long propagation lengths, this probably is not going to be great for you. However, if I want to have something that can strongly interact with a molecular species or increase absorption, this may not be so bad, because it's going to stay in the same place for a longer period of time and have a stronger interaction. So you can then, serious battery issues today, so hold on. There we go. No, that was just my computer hanging up. You can also look at the fringe or the phase variation, and you actually find that in the lower band, upper band, you have a negative fringe velocity, which basically means it has a negative phase velocity. This is just an interesting aside, but if you want to get to this race again and figure out how can I get phonon polaritons to win, of course I could try to speed them up. That means slowing down the dispersion. I just need a larger LO-TO phonon splitting. You can find that with various materials. Or I can try to find ways to compensate by increasing the lifetime. So we've been doing some recent work in collaboration with Jim Edgar's group at Kansas State and Dmitry Basov's group at now Columbia, where we've tried to improve this lifetime by reducing defects. So phonon scattering off these defects do play a role. If I look at Borne Nitride, the most predominant defect is actually an isotopic defect. So it's naturally 80% Borne 11, 20% Borne 10. That means, in effect, it's 20% defective, naturally, right? So if you make isotopically enriched materials, which I'm not going to say I know how to do other than get clean precursors, I'm going to leave that to Kansas State, you can get really high purities and really improve the phonon lifetimes. We're seeing values in the order of 2 to 4 times reduction in Raman line width, which means about a factor of 2 to 4 improvement in the phonon lifetime. And of course, you're drastically changing the mass. There's about a 10% change in mass going from Borne 10 to Borne 11. So you can also shift this Rostron band around, right? Just think of harmonic oscillators. However, something comes up when I start looking at the actual measured lifetimes, right? I can see I'm getting lifetimes from Raman that match up with this expected trend using first principles calculations, except when I get to really high purities. I would have expected about a 14-fold improvement in the lifetime. There's actually a break here from about 2 picoseconds to 7, right? That you would have anticipated, whereas our highest purity materials aren't nowhere near that. We seem to saturate at about 2 picosecond Raman lifetimes. So we did some secondary ion mass spectrometry and identified that there's actually, once you get to the point where you've reduced the isotopic defects enough, you start to find that you have a high carbon concentration, high oxygen concentrations, which then seem to be limiting this. So this gives hope, perhaps if we can start to reduce some of those defect densities, you could then get to the point where maybe you won't hit this 14-fold improvement, but if we get halfway there, this is a significant improvement. So that's just the phonon lifetime. Do we actually see any improvements in the phonon Polariton response, this hyperbolic response? And indeed we do. So this is, again, a scanning near-field optical microscope measurement from naturally abundant boron nitride. Here's the edge of a flake. We're launching off this time and measuring with the tip. See these interference fringes. And here it is for these enriched Borne 10 and enriched Borne 11. Right? It's more clearly observed the differences when you look at the line scans. Right? So you can see in the naturally abundant, this decays quite rapidly. These decay much slower. But you also see that you have these multiple frequency components embedded in this line scan. So if you actually extract from this propagation length or propagating figure of merit, you can see a significant improvement on the order of 2 to 4 times improvement over the naturally abundant systems. In fact, it doesn't quite reach up to what we would anticipate from the dielectric functions. We believe because the flakes aren't big enough to actually fully measure propagation, they actually reflect off the opposing edges and then interfere with each other in the center. But you also see those other frequency components, which are these higher order modes. And these exist for multiple cycles, right, that you don't observe in the naturally abundant systems. So now you can actually start to explore the physics of these hyperbolic systems in a very clean system, as well as looking at these higher order branches. And another way to do that is some work that we did looking at nanostructures of this. So these are boron nitride nanocones. This is the top of the cone. They have these conical shape sitting on a substrate. Again, here's my 2 Rostron bands. We'd obviously expect to have a resonant condition. You do. But there's some interesting effects. Unlike some of the phonon Polariton or traditional phonon Polariton systems, like say silicon carbide or plasma Polariton systems, like the metal structures, these have a strong polarization dependence. You see these modes predominantly when you have nominally normal in-plane polarization, nominally grazing incidence, out-of-plane polarization for the lower band. And you also see these higher order replicas, and they occur at higher frequencies like you might expect, but lower frequencies for this for the upper band. So this is higher order modes, higher confinement at smaller frequencies, right? It's kind of counterintuitive. So to understand what this hyperbolic nature really means, the first thing we did was we just said, what if we took the in-plane dielectric function and made it isotropic and calculate what we would expect to see, right? And you'd see something like this. Here's your spectra, here's your resonance. You have a couple higher order modes here. If I look at my electromagnetic fields, I'd have this highly surface confined field. If I look at the hyperbolic case, of course, these modes are now inside the material. And because of this angle dependence, I should get something that has this crosshatch field profile. And we saw this before. This is basically this, what's called anomalous reflections, or this frequency-dependent angle of propagation. But in this case, with flat films, I have no idea whether, as I launch this, if this anomalous reflection angle, this angle is conserved upon reflection. Is it launched here and then just randomly scatters based off of specular reflection? Or is it going to be maintaining and conserving this angle of propagation? The reason for that is anomalous and specular reflection are equivalent within a flat film, right? So I can show that I can change this initial propagation angle, but I can't differentiate whether the reflections are undergoing specular or anomalous reflection. So it turned out these nanocones, with their odd shape, actually provided a nice way to test this theory out. If I have true anomalous reflections that are conserved upon multiple reflections, I'd get this crosshatch-like field profile. If I end up with specular reflection taking over, I just get a random trajectory. Right? So we set out to do this. This is looking at scanning near-field optical microscopy measurements of these nanocones now. Shown in blue is the far field spectra. Shown in red is the spectrum measured with nano FTIR. It's just similar to SNOM, but now measuring the spectrum as opposed to the spatial distribution. The thing that we wanted to note was that, yes, there's going to be a spectral shift because I've changed the local environment, but I haven't changed the number of modes or the spectral shape. All right? I see the same number of resonances, and therefore, the tip itself is not inducing any new modes in the system. Therefore, I can look at these resonances and say, so what's going on here, right? And so if I take one of these guys, this one right here, I can look, because of this tilted angle of the sidewall, I can get my tip in and actually measure what's going on there. I can directly measure the electromagnetic fields and how they're redistributed in the sample. So this is the substrate. Here's the top of the cone. This is the base of the cone. And what you find is that basically I observe these hot rings, these alternating fields of high and low field along these edges, and the number of these increases as I go to higher order, right? And if I do electromagnetic simulations from the top down, it's exactly what I would expect. And therefore, if you actually observe in this, this would be these propagation angles dictated by that tan theta equation. And now, showing that this should continue these anomalous reflections and conserve that angle. So by extrapolating off the shape of this nanocone where these reflections occur, I can compare to that and show that, yes, no matter what, independent of the number of reflections that this undergoes within your structure, this is going to be maintained, which means this is going to be robust for things such as a hyperlens, right? So I can scatter off of a deeply subdiffractional object, launch these hyperbolic polaritons, and then directly image them on the opposite surface. And by changing the frequency, we won't call it exactly magnification, but change the projection of that image onto the top surface, right? And this is something that we observed. I won't go into too much detail, but this is some work I did with Thomas Taubner's group. Similar work from Dmitry Basov's group came out at roughly the same time. And the key point here is this gives you the ability to have a lens that can image really small objects with far field, long wavelengths of light. So in this case, we were able to image a 100 nanometer object using 13 micron wavelengths of light, using only a flat slab of Borne nitride, no patterning involved. Now that's just Borne nitride. So just like graphene was just an exemplary case for surface plasmons, we also have Borne nitride as an exemplary case, not only for phonon polaritons and 2D materials, but for these hyperbolic systems. And now you can see a broad range of these different systems from molydisulfide, graphite, tetradiamites, some of these multiple layered compounds. There's actually been a compendium of naturally hyperbolic systems that's been reported. Many of these are layered materials. I'm sure now there's many more in this much further expanded list because of this anisotropy. So there's a broad range of different types of polaritonic physics that can allow this to extend over a very broad spectral range. So while phonon polaritons are limited because of the natural frequencies of optic phonons to about, say, 6 microns, by using plasmon polaritons, exciton polaritons, things like this, you can spread this over a much broader frequency range. And new materials are being discovered all the time. So I actually had the good fortune to work with Josh Robinson and Joan Redwing at Penn State, where they were able to grow two-dimensional gallium nitride. This is a bilayer of gallium nitride encapsulated with graphene that actually shows the same quantum confinement effects that you'd expect from this. We're currently trying to see if we can't look at some of the phonon properties under these systems as well. So with that, I don't know how much time I have. Okay, so I'm going to breeze through this. This is just where I see things going, right? Everybody talks about atomic scale, or talking about heterostructure systems. Within the context of nanophotonics, this can give a lot of functionality, right? The reason being, in this case, if I can couple, say, phonon, plasmon, polaritons, I can create a hybridized mode that has some of the character of both. And there's precedent in the literature, going back You want to find anything, like a previous speaker said, go back to the 1950s and just find when it was done. You can just look at LO phonon plasma coupling and polar semiconductors. And this is roughly the same concept. And therefore, not only can this be done in 2D materials, but this could also be done in, say, potentially be done in atomic scale heterostructures, right, of more traditional semiconductor systems. And this has been demonstrated for graphene. Here's the dispersion relationships for graphene and Borne nitride. Here's this hybridized system. This was predicted by Frank Koppen's group, later demonstrated by Dmitry Basov's group. The only thing I want to really point out here is the additional functionality this gains. You get basically this tunable phonon-plasmon polariton. By changing the Fermi energy, you can now tune the hyperbolic behavior of this mode. Basically, this mode is still confined in the volume of the Borne nitride, not in the graphene. And therefore, something that has a 6 electron volt band gap, or roughly 5.5 maybe, you can now gate tune using the gate voltages required on graphene. So it gives you active control of this. And oddly, because you're averaging both the group velocity and the phonon lifetimes, the polariton lifetimes, you get longer propagation lengths in either of the two constituents. And then you can play with the symmetry of these modes and broaden the range of these interactions. The other type of hybrid that could provide some additional functionality, perhaps changing band gaps to couple with these phonon polariton systems, is to look at these highly confined structures. And we have some initial evidence of this where basically you can look at these hybrid modes within, because you're now modifying the phonon density of states by using interfaces and confined structures. You can therefore change the phonon density of states and therefore result in a hybrid mode that's now gives you new dielectric function. And I'm not going to go through this. I'll tell you it works. If you really want to know, I'm more than happy to show you the results. But it gives you some really exciting results where you can actually tune and change the dielectric function. The question now is twofold. We demonstrated this in aluminum nitride, gallium nitride. We're working on the paper for this right now. The question is, can you actually dictate it? Can you control this dielectric function before the fact? Or do you just get whatever random structure you made? And can we start looking at structures where there is no covalent bonding out of plane and still result in these types of interactions? So I'll close with this. Of course, you have a broad range of these different polaritons. It's now broadening every day by looking at these coupled modes. Right? And this can add a great deal of additional functionality. Of course, I need to thank my collaborators. I've had a broad range of folks that I've worked with. And I also want to thank specifically Dmitry Basov. He provided a couple of the slides, so I didn't have to remake them from scratch. And some of Tony's talk previously, so I didn't have to make that from scratch either. So thanks. So apparently the Anchorman may not be the fastest. So. Everybody wants dinner.
Yep. All right, so I think we can take the question offline. And so this brings us to the end of the day 1 summer school, and I think we have some announcements.
Yeah, just make a couple of announcements. First, and this is primarily for the people. Anyone can fill out one of these questionnaire forms about today's sessions, but particularly the students